It's an incredibly exciting time to be working in quantum computation right now because we're starting to enter the era of quantum error correction in practice, in hardware. So if you've maybe went to QIP this year, then you can see, would have seen some fantastic work by the Harvard QERA group on realizing logical quantum error correction gates in their neutral atom architecture. And actually just today, the Google team uploaded a really interesting paper on realizing surface codes in their hardware architecture. So it's starting to become real. It's always been this long distance dream that, one day we would build these logical gates and they would have significantly better error rates. Now this dream is starting to become something that we're actually starting to build towards. Now, of course, at IBM, we are also want to be a part of this. We understand that in order to make quantum error correction practical and useful, error correction is definitely part of that strategy. And fortunately, there's been a lot of progress, not just in the experimental areas, but also in theory. So let me outline a couple of recent theoretical results. So in theory, in the theory of quantum error correction codes, really a lot of progress has been made recently. We've learned how to generate quantum error correction codes with significantly better properties and significantly higher efficiency than surface codes, which are the previously most leading proposal. So there are some families of quantum error correction codes whose number of logical qubits starts to scale linearly in the number of physical qubits. So they have something called constant rate. And similarly, you get large amounts of protection of that data as you scale the number of physical qubits as well. So this is something in particular that the surface code does not achieve. The surface code has a constant number of physical qubits, a constant number of logical qubits. And second of all, so it has something called vanishing rate. And similarly, the amount of physical qubits you need for a distance D protection scales quadratically in the distance. So as a result, like all of these benchmark results that look into how many physical qubits would you need to actually run Shor's algorithm give you these ridiculous predictions of the millions or hundreds of millions of physical qubits. We would like to do better. So for this reason, we're interested in these improved families of quantum error correction codes, but also we're interested in small examples. So suppose you wanted to build one of these improved low density parity check codes today. What is a small example of such a code that you might want to build? So I'm particularly excited about this bivariate bicycle family. So this is a family of quantum error correction codes that leverage long-range connectivity, connections between qubits that are far apart from one another on a chip, to give you significantly improved encoding rates. So for example, if compared to a surface code with a similar number of logical qubits and a similar distance, this uses about a factor of 10 fewer physical qubits in order to realize that. So I find this code family incredibly exciting, and in particular, I'm very interested in this 144 1212 code that we've been calling the gross code. Gross is, it means a dozen dozens, so 144. So I really hope that at IBM we can build one of these codes someday. And I'm really more of an algorithms guy. I have only done work on quantum error correction very recently. And the reason why I'm coming to this research area is because I want to know what my architecture is. I want to know what basic instruction set am I compiling my quantum algorithms to. So my question is, how do I perform logical gates on these new quantum low density parity check codes that have been developed over the past couple of years? So what do we know so far? So we have a couple of techniques for implementing logical gates that are efficient, but don't give you enough gates to really do logical computation. So an obvious observation is that a lot of these codes are CSS codes. CSS codes naturally have transversal CNOT gates. So that gives you some number of gates right out of the box. Another really interesting family of techniques came from a paper by Berkman and Burton. So they have a paper on fault transversal logical gates, and they rely essentially on physically permuting the physical qubits that constitute the code in order to realize certain logical gates within the code. So there's a couple of very interesting and high efficiency gates that you can implement this way. In particular, this family of automorphism gates is very interesting. It exploits the sort of toroidal structure of these bivariate bicycle codes. You should sort of shift the qubits along the torus and implement logical gates this way. However, they also only give you a relatively small family of gates to work with. So that's efficient but insufficient. We also have a sufficient but inefficient approach, and that's just to let a surface code do it. So if we don't know how to do logical computation on one of these QLDPC codes, we can still use a QLDPC code as a memory, as sort of a data bank that can store our logical qubits while we're not doing computation on them. And then we swap them in and out, load them into the surface code whenever we want to perform computation, and then load them back. So this works. We know how to do logical gates in surface codes. However, now we've lost all of the efficiency improvements that we wanted to obtain by switching to this new family of codes. So on the one hand, these surface codes, they have this quadratic scaling in the number of physical qubits with the distance. So that's a thing that we wanted to get rid of. But also the tool that we're using to send data in and out of the code, it's one of these Ancilla systems that was developed by Cohen, Kim, Bartlett, and Brown, is absolutely massive. So it has 1,300 physical qubits or so. This LDPC memory, it has 144 logical physical qubits in it. You can include check qubits, it gets you to around 300 physical qubits. So the tool that you're using to load data in and out, the wire that's connecting your surface code to your memory, has an order of magnitude more physical qubits in it than the actual data bank itself. So this is, it's incredibly inefficient in comparison to what the memory bank would be capable on its own. We'd really love to be able to do computation on the memory bank directly. And that's really what I'm going to be talking about today. How do we achieve logical gates without all of this overhead? So the tool that we're going to be relying on and trying to improve are these Cohen Ancilla systems. So these essentially take your quantum error correction code and add a bunch of additional physical qubits and checks to make a new code that now lets you measure certain logical operators. So the logical gate that we gain access to with these Ancilla systems is a measurement. It will be measurement-based quantum computation in many ways like lattice surgery. So it should be familiar if you're familiar with lattice surgery. So let's look briefly into how this Cohen scheme works. So let's consider a quantum error correction code down here. I'm going to be using this Tanner graph formalism. So the circles represent physical qubits and the squares represent checks. And if a check is connected to a qubit, that means that that check vertex has support there. So for example, this Z check right here performs a Z parity check here, here, and here. So Z, Z, Z. That would be a stabilizer within this code. Tanner graphs are very nice because they let me very succinctly and graphically describe quantum error correction codes. They're also particularly interesting for us folks in the business of building superconducting quantum computers because they tell you exactly what you need to build. You need one physical qubit for each of the data qubits, obviously, but also for one of the checks. So suppose we had a quantum error correction code here that featured a particular X-type logical operator. So an X operator that's supported on these 4 physical qubits at the bottom. And we wanted to measure that operator. Well, in the Cohen scheme, we staple on a bunch of additional physical qubits and checks. So if you look at the product of these X checks at the top, you can see that their support will cancel if you multiply them all together on the top qubits. And on the bottom qubits will give you precisely the operator that we wanted to measure. So now we've made a new quantum error correction code that has the logical operator as a stabilizer. So hence switching to this code is going to measure this logical operator for us. The purpose of these additional physical qubits on the top is just to make sure that all of the checks commute. So if we didn't have these additional checks, then these X checks and the Z checks that were already part of the error correction code would not be commuting with one another. So wouldn't it be great if this were actually the Cohen construction? Look how efficient this is. We have a operator, a logical operator of weight D here, and we added, roughly order of D many additional qubits to the scheme in order to measure the operator. The problem is that this isn't necessarily fault tolerant. Switching to this new code might actually reduce the weight of some of the logical operators within the code, within the combined system. and hence not and hence damage the other qubits in the process. So in order to fix this, Cohen and co-authors essentially stapled on order of d additional layers on top. So we're just going to alternate between this conjugated X-type layer and then the Z-type layer again, and just do this order of d many times to build this tall tower. And now we're back in order of d squared land. We're basically back in surface code land in terms of the efficiency of the scheme. So essentially, the majority of our work was figuring out how you can get away with fewer layers. So we have two results. One is for general quantum error correction codes. This is a recipe that you could apply to any LDPC code. And in particular, we connect this number of layers to the expansion properties of the quantum error of the subgraph that's associated with the operator. So what do I mean by subgraph of the measured operator? Let's go back to this original code here. I didn't show all of it. I only showed the subgraph that was relevant to the support of the logical operator that I wanted to measure. So the physical qubits on which the X operator is supported and all of the Z qubits in its neighborhood. That's the sort of subgraph that I'm interested in. And if that subgraph has a large boundary tier constant, so has good expansion properties, that gives me a bound on how many layers of this ancilla system that I need in order to achieve fault tolerance. So that's sort of our main theoretical result. And then, of course, we apply this to this gross code. So we give a particular example of logical operators that you can measure using an ancilla system with really not too many additional qubits, another 100 physical qubits that are required. So both checks and for checks and for additional data qubits. And this gives you access to some family of quantum measurements on your code. And we show that this family of measurements suffices to implement Clifford gates on all but one of the logical qubits within the code. So let's talk about this first part. I'm only going to go into, I'm going to present the proof at a very high level. I want to show a couple of ideas that went into the construction, but I'm not going to get too nitty gritty. There's three ideas that went into these layer count reducing arguments. So one was removing gauge operators from the system. Additional gauge degrees of freedom get introduced when you perform this construction, and those might not necessarily be error protected. So those might interfere with the existing data, with the data that's already stored in the code. Second, I want to give you this argument of why expansion properties of that subsystem give you a reduced layer count. And finally, I want to extend this technique to not just being able to measure single X operators. I want to be able to measure parities of multiple operators simultaneously. I want to be able to measure Y operators that are products of an X and a Z operator. I want to be able to do more complicated things. And in order to make all those things fault tolerant, it was necessary to come up with this idea of a bridge system. So let's go through all three of these ideas briefly. So I mentioned these gauge operators here. Maybe let's look at this particular code in a little bit of detail. You can see how these ZZ polymatrices, they commute with the stabilizer, they commute with these X checks, but they're not in the stabilizer themselves. So that means there's an extra logical qubit that we introduced here. And since these operators have low weight, these logical qubits are not error protected. So, that's fine, right? As long as that doesn't interfere with anything else. Well, any logical Z degree of freedom also has a logical X degree of freedom that, is associated with that qubit, right? A logical qubit is defined by its X and Z polystring. And that X string might absolutely leak into the rest of the system, multiply onto some other X operator that we want to protect. And now we have a combined degree of freedom that might be lower weight. So these gauge operators are a huge problem. The way that Cohen solved this, again, was by introducing a bunch of additional layers. This makes these X chains really long, and hence prevents them from reducing the weight of anything they multiply onto. We instead just get rid of the gauge operators by introducing additional stabilizers. So, you don't like gauge operators, just put them in the stabilizer. Next, let's talk about expansion. So this boundary Cheeger constant essentially measures how quickly the neighborhood of a set of vertices grows. So here we're interested in bipartite graphs just because Tanner graphs happen to be bipartite. We might be interested in a family of X checks. How many physical qubits are in the neighborhood of that family of X checks? That ratio between these two quantities, that's going to wind up being important for us. So here we have like one of these multi-layer constructions of an ancilla system. We might have a logical X operator, not the one we're trying to measure, just a different logical X operator. And we want to make sure that we don't reduce the weight of this X operator by multiplying additional X operators onto it. So here we might take this X stabilizer right here and multiply it onto here. When we do that, we move the support into a higher level on the ancilla system. But we also introduce some support down here. And the amount of support that we accumulate down here can be bounded by, can be analyzed in terms of the Cheever constant of the support of the operator up here, right? It's the neighborhood of the X checks that we multiplied on. So every time we do that, we'll just keep doing this until we'll keep doing this, moving the X operator all the way to the top, in which it actually loses its support on that part of the system. But we've accumulated a bit of a slime trail on the bottom half of the system. And that accumulation sort of means that we don't need that many layers, right? The larger the support is down here, the fewer layers we need. Finally, let's talk about bridge systems. So one thing that was already known in the literature, as far as I know, is that you can take two of these ancilla systems and staple them together by adding a bunch of bridge qubits connecting each of the pairs of checks. So this will actually give you a joint system that will measure this parity X tensor product X in two different codes. So that's pretty neat, but it turns out that this is actually necessary to do Y measurements within the same code. So here we have two logical operators, a logical X operator and a logical Z operator. We can measure the logical Z operator in a very similar way of measuring the logical X operator. We just need to swap the roles of the checks. So we're interested in the X checks in the neighborhood of the Z support. And then all the checks up in the ancilla system will be Z checks. So we can't use these two operators to make a Y operator because they commute. But suppose they had a qubit of overlap, then their product would have Y support on this middle qubit. So this would correspond to a logical Y operator. And similarly, the corresponding check in the ancilla system would be like a mixed type check. It would have Y support on this physical qubit within the code, and then X support on the X system, Z support on the Z system. So, this is all well and good. This has the desired Y operator as a stabilizer, but how do we show that it's fault tolerant? Well, in part of this measurement procedure, you need to actually show that every logical operator, even the ones that are not in the stabilizer anymore, remain high weight throughout the entire code deformation procedure. And it turns out that that doesn't happen. So let's look at the Z qubit, this Z logical here. Let's multiply it by all of the Z checks and also this mixed type check. When we get this product, we get this operator. This is weight 2. So we have a source of error, right? It only takes 2 physical errors in order to flip this check, flip this logical operator. So that won't do. So the way that we fix that is by introducing the bridge again. So now when we multiply by all of these Z checks, we accumulate support up in the bridge, and that prevents the operator from being low weight. So that's really the end of the technical part of the talk. So these were sort of a rough whirlwind tour of the techniques that went into these ancilla system reduction techniques. Let's finish up by showing the spoils essentially for this 144.12.12 code. So we start by picking 2 logical operators, a logical X operator and a logical Z operator that anti-commute. So there's one logical qubit that we can measure. And we make the X system and the Z system that's associated with these 2 operators. You can see because they anti-commute in one spot, they have one overlapping qubit. in order to measure the corresponding y operator, we will also need to introduce a bridge. So we can measure 1 qubit in the x, y, and z basis. That's not a lot. So how do we get from there to all Clifford gates? Well, one thing we can do is we can exploit a particular symmetry that this code has. If we take the transpose of this torus and also Hadamard everything, that actually takes the code to itself and gives you access to other logical qubits. So if we perform that transformation to this x and z operator, we get a different logical qubit with the exact same geometry, with a subgraph that is isomorphic. So we can actually take the same ancilla system and connect it in 2 spots and use the same qubits to measure more operators. And we can also measure parities between these operators now. So now we've gone from 1 logical qubit to 2. We have this family of 8 different operators we can measure. Finally, we're going to bring these automorphisms back into the picture. So this was a small set of logical operators that is transversal and is easy to realize directly on the code itself. And we're going to conjugate our measurements via these automorphism gates. There's 36 of these automorphism gates, so we get a family of 288 different measurements. And finally, if you want a unitary gate set, you can convert measurements into polyrotations, a particular kind of Clifford gate, using a relatively standard measurement to rotation conversion circuit. So this measurement to rotation conversion circuit requires 1 ancilla qubit right here, and that ancilla qubit is the reason that we need that ancilla qubit is that, whenever you perform a measurement, you lose some information. So if we want to have a subsystem where we don't damage the quantum information, then it's always necessary to have an additional degree of freedom that sort of gets measured. So that's why we can only do Clifford gates on 11 of the 12 logical qubits. There's one of the qubits, that 12th qubit is being put to work. Okay, well, thank you very much for your attention.